Today I want to talk a little about my science research, give you some basic concepts of mechanics of thin film materials. So what is thin film? Thin film is two-dimensional material created by deposition of atoms on substrate, and we have different mechanism of it. So we can use heat to vapor the material that then we deposit it on the on substrate, or we can use different chemical reactions for that. But finally, we get some structures that you can see on this figure. It's very complicated structures that we use in microelectronics, in optics, in I don't know, in medicine. Actually, such kind of materials we can use everywhere. And if we talk about surfaces of different solids, true to say, it's also a film that have different properties, and these properties depends on different structures and so on. So I want to show you a first stage of film deposition. It's a model. Here we go. It's looped. So atoms group in structures, in some clusters, and then these clusters group on bigger and bigger structures, and then we have the film on the substrate. So what is the point, and what is the main problem of such methods? Actually, film exhibit unique properties. These properties we can use to improve, for example, friction, wear resistance, hardness. Also, we can use these properties to protect materials from different environments, and so on. Also, such kind of fabrication of films produce so-called size effects. So this is some kind of characteristics of which depends on thickness, crystalline orientation, and multilayered aspects. So we can design new materials, for example, use different layers with different properties, but overall we have new properties of such kind of materials. But okay, yeah. We can use these materials, as I said, in micro devices. So we can use for biological sensors. You know, we use it in solar batteries, in hard disk drive, and so on. But there is a problem that connected with fabrication of such kind of materials. As you can see, when we developed thin film, we have some relief on the surface, or even on the interface. So here you can see the cross section of the film that was grown on the substrate, that it was annealed, and we have some waveness on free surface. This defect can decrease mechanical properties, electrical properties, optical properties, and so on. And we need to predict when we have such kind of waves and what properties we have when we have perturbate surface and so on. So we need to model such kind of materials. We need some mathematical calculations for this. And today I want to talk briefly about some methods which we use to predict such kind of defects and calculate the properties of it. The fabrication of thin film typically results on high-level stresses, intrinsic stresses that connected with development of film materials. So as you can see on this figure, we have some lattice mismatch because we have different materials for substrates with some lattice constants, another material which have different lattice constant as a film. And finally, if we want to connect to each other, we need to stress, for example, film. So here you can see that top layer is a little bit stressed. Also, we have another kind of stresses. It's extrinsic stresses, which result from mismatch of thermal coefficients. For example, if we want to annul this structure, one material will deformed much more than other materials, so we have the stresses in this region also. So the theoretical and experimental studies show us that stress surface become unstable due to surface diffusion, and this process can generate different defects like vacations, dislocations, microcracks. So here we have also a big problem. For example, here you can see the dislocation near the interface of film and substrate. What is the dislocation? Dislocation is distortion. This is the distortion of crystal structure of for example, film or substrate. So another defect is microcracks. So they can be nucleated on the free surface of the film, and when we, for example, load our structure or our device, it could be totally cracked due to such kind of defects. I have another movie to show you how defects grow, how they affect on our film structure.
Why is that so green? Okay.
I don't know. On this video we can see how the film debonding from the substrate, and here, as you can see, we have some microcrack. So it's not so good for devices that based on film materials. Another defect is nucleation of micropores. And also on this video we can see nucleation of microcracks here on the free surface, and also you can see, I hope you can see, because it's not so clear, but here we have some distortion of our crystal structure, its dislocations, and then they can produce also different stress effects. But on the other hand, yeah, it's molecular dynamic simulation, so we can simulate this process and we can change properties of materials and different load states and see what we get, for example, if we try to stress nickel or, I don't know, aluminum or something like that. So it's a very useful tool, and in 5 minutes I try to talk about it as well as other methods of calculation. But on the other hand, if we can control these processes, we can use it for fabrication of different structures, nanostructures, for example, like nanosprings, quantum dots. It's, as you can see, very small structures. They have very special optical properties and can be used in different sensors. Also, we can use, we can product some nanoporous materials and nanotubes. And we can build some devices with these technologies also. So the main point, we should control these processes and we should know what properties we can get. And the first part of methods that I want to talk today, that we can use to solve such kind of problems, it's continuum-based models. Recently, these models were used to explore different physical parameters such as film substrate stiffness, stress states, lattice and thermal mismatch, geometrical parameters such as film thickness, profile, for example, profile of undulation. So we can explore how these parameters affect on stress concentration, on field illumination, on surface pattern formation, and so on. For example, on this picture, we can see the stress concentration caused by the wavy surface. What is the stress concentration? For example, if we take this piece of paper, it's very hard to break. As you can see, it's very solid. But if we made some surface defect, for example, we can make such kind of notch, it will be quite easy to break it. Why so? Because wavy surface generate very high stresses. So, for example, if we in this picture we can see that stresses in this region in three times bigger than in other regions. For example, if we made much different patterns, stresses can increase in 10 times or in 15 times or so on. So This simulation we made with finite element method, so it's also continuum-based model, and now I will talk about these models. I talked recently about stress, mechanical stress, but what is this? Mechanical stress is some kind of abstraction that we use to model the interatomic forces. So in macro scale, we don't need detailed description of particle interaction, and we can use such kinds of abstractions. So we can, all the material can be viewed as a continuum of points. And we can use stress to describe how the forces in our material interact with the body. So here we have a little math description of this abstraction. As you can see, we have some forces in small region, and we can use the limit as this area shrinks to 0, and in this case we obtain the definition of stress. If we will use the Cartesian coordinate system, we can have 9 different stresses that act in bodies. Another abstraction is the strain. It's the macroscopic measure of deformation, and deformation is presented as displacement between different particles of solid. So we can write the numerical values of the displacement in this case, and if we make neglect some products in these quantities, we obtain linearized strains, and these strains we can use in generalized Hooke law that can describe how material react on different actions, on different forces, on different loadings, and so on. So I think that you should know the Hooke law from the school. When you take the spring with different properties, you can use the same force, but different springs will have different deformations. And the same concept we can use in a whole solid body, but it's more complicated. We can write it in this way. So here we have our 9, for example, 9 stresses, and it's related to 9 component of deformation of deformation tensor, and these two will use connected with material constants. If we use these conditions of some kind of relation, we will have 36 different constants to obtain this law. But actually we have different materials, and for example, for isotropic materials that have the same properties in every direction, we need only two of these constants. So, the main problem to solve these equations, as you can see, we have partial differential equations, and we need to solve them. If we talk about simple task, for example, we want to see how the bar stretched, we can use different analytical models and try to get the exact solution of these equations. But if we have some, for example, some waveness or some different structures on the surface, it's not so easy to get the exact solution, and we need to use some computational models, some computational methods, and one of such kind of methods is finite element method. So what is the main point of this method? We can discretize our system on small pieces, on small elements, and try to use simple solution for these elements, and then we can use these simple solutions for whole body. As you can see, we can describe the displacement of each point of such kind of element in this way. So here we have on the left side some function, it's a displacement vector, and on the right hand side we have some shape functions, and here we have a vector of displacement of nodes. So finally we can find the displacement of these nodes, and then on these values we can build a whole function that give the displacement of each point, for example, of this element, and finally we get the displacement of each point of our whole system. I'll try not to bore you a lot, so we have some flow of this process, but in the end we get the system of linear algebraic equations that give us the displacement of each node. So, and if we know these quantities, we can get back. Get back and get this function for whole system. Sounds nice. But these methods have one big disadvantage. We can use it for nanostructures, where we can we need to know some specific properties. And maybe, as you know, these structures, even they made from the same material, they have different properties. For example, if we take the tube on a microscale and nanotube from I don't know, from aluminum, for example, they will have different properties, and properties of nanostructures can't be described by continuum models. So it was shown in different experimental and theoretical works. For example, we can mention here the work of Kamaret and Siratsky. They predicted that, theoretically predicted that elastic models can be enhanced or reduced even on 20%. When the thickness of our film reduced to below 5 nanometers. And Fertesh and the Fertesh group confirmed this result by experiments for different multilayered structures. For these materials, these structures, we can use another method. It's MD simulation, and I've demonstrated to you 10 minutes ago. In solids, atoms are very closely packed, and average distance between them it's about a few angstroms. But the radius of atomic nucleus much smaller. So as you can see, it's in 1,000 times smaller. So we can make some model that's based on point representation. So the atoms can be represented as a point mass, as in classical physics, classical mechanics, and we can model this system as classical particles. So here you can use, here you can see that we use this system of particles, can describe how the material deformed, what forces are between the particles, and so on. For description of such kind of systems, we can use only Newton's law. So we can write this law for each particle of the system, and we get the governing equations that give us the dynamics of this system. So here the system of the equation that we want to solve, and this equation can be solved by discretizing in time. So we can make some small steps and get the trajectories of atoms and different forces and so on. But the main problem of this method, how we should describe the interaction between the atoms, how we could choose the forces. And there are a lot of different functions that can describe the energy that bond that formed between two atoms. This function can be get from experiments. So we use different techniques to get the parameters. Also, these functions can get from theoretical approximations. For example, we can use quantum mechanics equations to describe how atoms interact between each other. But finally, if we know these functions, we can solve this system. So we know the masses, we know this function that hide the forces, and solve this. We know how each atoms move, how each atom interact with each other, and we can see on. I show you again. So we can see how the material, for example, breaks, or how the dislocation forms, or things like that. Another example, for example, we can see how the pores in material bifurcate, and here we can see some nucleation of cracks and so on. So it's a very useful method, but it also has one big disadvantage. Even if we use high-end parallel supercomputers to solve such kind of problems, we can simulate the systems that have the order of 10 and 9th degree of atoms. So it's a very small volume. And we can describe other effects. And what we can do with this? The main challenge of recent studies in mechanics of solids, in mechanics of thin film materials, to connect these different methods and to integrate this method in various scales. So we can use continuum theories for microscales, and when we get to nanoscale, for example, we can encapsulate in our classical theories MD simulations or quantum mechanics models, and in this way we can describe different systems and different effects. So it's, as I said, it's a main challenge in my science, how to connect all these methods in one system. Okay, I finish. So if you have some questions, I will kindly